Good morning everyone. Today we'll discuss about third module of fluid mechanics, that is fluid dynamics. So what is fluid dynamics? The fluid dynamics is the study of force which produced motion in a fluid. So study of these forces is called as fluid dynamics. So it depends on the Newton's second law of motion, which is the fundamental principles on which the fluid dynamics are based. So what it states, the- it states that the resultant force on a fluid element is directly proportional to the rate of change of momentum and takes place in the direction of force. So therefore the net force equals to mass into accelerations. It is a product of mass into accelerations. So what are the forces acting on the fluid? The first force is a gravity force. It is represented by Fg. It is due to the weight of the fluid. Next is pressure force, that is nothing but Fp. It is due to the pressure gradient between 2 points in the direction of flow. So that is represented by Fp. So next third one is viscous force, that is represented by Fv. It is due to the viscous property of the flowing fluid. Next fourth one is turbulent force, that is represented by Ft. It is due to the turbulence of flow, which is represented by Ft. So next one is fifth one is compressibility force, that is represented by Fc. It is due to the elastic property of fluid. So overall the net force equals to the summation of all the five forces, that is net force equals to Fg, Fp, Fv, Ft and Fc. So next let's see the conditions on net force is depends. The first condition is that if the compressibility effect on the fluid is negligible, it means that the term Fc becomes 0. There net force becomes the summation of Fg plus Fp plus Fv plus Ft. So I have been represented this equation as equation number 2. The equation number 2 is called as the Reynolds equation of motions. It is useful in the study of the turbulent flows. Next condition is if the compressibility and turbulence effect on the fluid is neglected. It means that the term of Fc and Ft are getting neglected. Then the equation becomes the overall net force becomes the summation of Fg plus Fp plus Fv. That is equation number 3. This equation number 3 is called as Navier-Stokes equation of motions. It is useful in the study of viscous flows. Next, if the fluid is considered to be an ideal flow, then what is ideal flow? Ideal flow which doesn't have any turbulence, compressibility and viscous force. It means that all the three terms get neglected. So only the remaining forces are the gravity force and pressure force. Therefore, the net force becomes equals to the summation of Fg plus Fp. So I have represented this equation as equation number 4. This equation number 4 is called as Euler's equation of motions. It is useful in the study of ideal fluid and also in real fluid where viscous force is negligible. So next we study about impulse momentum principles. So it is based on the law of conservation of momentum, which states that the net force acting on a fluid mass is equals to the change in momentum of flow per unit time in that directions. It is based on the Newton's law of motions where F equals to the product of m into a, where acceleration, a for acceleration we can write change in velocity by change in time. So a equals to dv by dt. So therefore F equals to m into dv by dt. Next we can substitute. Okay, so let m will be considered as a constant, so therefore I can write F equals to d by dt of m into v. So this is known as momentum equations. So if you take dt on other side, it becomes F into dt equals to d of m into v. This is known as impulse momentum principles. So it states that the force F acting on a fluid mass m in a short interval of time dt is equals to the change in momentum, that is the change in momentum is given by d into m into v, that is delta mv in the direction of force. Next, what are the applications of momentum equations? The applications of momentum equations is used to determine the resultant force exerted on the boundaries of flow passage by a stream of flowing fluid as the flow changes its direction or the magnitude of velocity, or it may be both. The practical applications are as follows. It may be used in the agricultures, in the different industries. So we'll find the various applications. There as follows. First one is the flow through the bent pipes. Next one is jet propulsions and propellers. Third one is fluid flow through stationary and moving plates. Fourth one is non-uniform flow through sudden enlarged pipes. Next, we'll see about the very important concept, that Euler's equation of motions. That is, before to this, today we'll discuss about the Bernoulli's equations, which is very important principle on which various measuring instruments are depends. So before to this, before deriving the Bernoulli's equations, we have to derive with the Euler's equation of motions. So therefore we derive the Euler's equation of motion, then integrating that equations to get the Bernoulli's equations. Okay, let's consider this figure and all these things. So here the equation in which, as I said you, the Euler's equations, it is a combination of force due to gravity and pressure force, where the fluid is considered to be ideal. So this is the first conditions we are going to consider. Okay. Next, consider a streamline in which flow takes place in a S directions. It is as shown in the figure. Next, consider a cylindrical element of cross section area dA and length ds. It is as shown in the figure. So here we know that let the pressure force in the direction of flow, that is P into dA. How it is came? So we already know the pressure is given by the force by area. The pressure force equals to, it is Fp into A. Already we are having a considering a small section area, that is dA. So then the F becomes P into dA. And in the same opposite direction we are having the direction of flow, which is taken to be P plus delta P by delta S into ds into dA. So here P is taken plus partially it is moving dou P by dou S with respect to length ds. So this is a pressure force acting in opposite direction into area. And the third force is the self weight, which is acting due to the gravity. So we know that W is m into g, that is mass into accelerations. So we already know that density equals to mass by volume. For mass I can write rho into V. What is V? V is nothing but a volume. Volume can be given as the product of dA into ds. We are having rho g dA into ds. That will become the self weight of the elements. considering the theta be the angle between the direction of flow and the weight. Next, by Newton's second law of motions, as already we know that the net force in the direction of flow is equals to the summation of mass of the fluid element and acceleration in the direction of flow. So we have to consider in these equations. So this is a, if it is moving on, P will be, P into dA will be taken as a positive and opposite side will be taken as a negative in this sign conventions. So we are having a weight. Weight is taken to be a self weight. We have to resolve the components. After resolving the components, it becomes W cos theta on horizontally opposite to the P into dA. So here next we are resolving, equating all the forces. Okay, the net force, we have to add the net forces. So P into dA minus, why it is minus, taking in a opposite direction, P plus dou P by dou S into ds with respect to dA minus rho g into dA into ds into cos theta, which is equals to mass into accelerations. So mass is given by rho into V. Rho is density, volume is dA into ds. Here ES is acceleration in the streamline. After simplifying, we are having P into dA minus P into dA, that will get cancelled out. Here minus minus sign there, minus into plus, minus it is there, minus dou P by dou S into ds into dA, minus it is there as it is, and it is as it is. I represented this as a equation number 1. So next, dividing throughout the equation number 1 by ds into dA, that is nothing but a volume to the above equations. So what is get, the dA into ds is common throughout the equations. After dividing, it becomes minus dou P by dou S minus rho g cos theta equals to rho into as. So as we all know, the acceleration is the change in velocity by change in time, and where velocity is the function of distance and time. So that we can write, we know that ds by dt equals to velocity. So next we can write acceleration as a function of distance and time. So dou E by dou S into ds by dt plus dou E by dou t. Okay, this is a chain rule. Next, we already know the ds by dt is nothing but a v, and it becomes like this. Next, we are considering it as in a steady state. What is steady state? The velocity of the fluid is remain constant. It not vary with respect to time. So therefore, the term dou V by dou t becomes 0. Next, the acceleration term becomes V into dou V by dou S. Now we consider the figure. So it becomes like this: ds into theta here it is, and with respect to perpendicular small distance, that is dz. So cos theta becomes dz by ds. Next, substituting this equation number 2, we are having cos theta, we are replacing with this term. Okay, so ds by dz by ds. So after substituting in these equations, we are substituted minus dou P by dou S minus rho G into dz by ds minus rho V into dou V by dou S equals to 0. So next, all it is there with it is there, we are multiplied with minus sign throughout, it becomes a positive. So therefore the equation means dou p by dou s plus rho g into dz by ds plus rho v into dou v by dou s equals to 0. So oversimplified, okay, taken on other side, it becomes dou p by dou p plus rho g into dz plus rho v into dv equals to 0. Throughout, next is the dividing by density throughout the equations, then becomes dou p by rho plus g into dz plus v into dv equals to 0. So this equation is called as Euler's equation of motions. So next, after Euler's equation of, once we get the Euler's equations, it's very easy to get the Bernoulli's equations. What we have to do? We have to consider, we have to integrate this above term Euler's equations to get the entire Bernoulli's equations. So Bernoulli's equation of flow from the Euler's equations. So as it is there, the Bernoulli's equation is based on the Euler's theory of fluid flow, and it is obtained by integrating the Euler's equation of motions. So it is dou p by rho plus g into dz plus v into dv. Integrating the whole terms. So next, so for the incompressible flow, the density remains constant. It is a constant value. Okay. So if you integrate all the terms, it becomes dp. So integration of this is p by rho. This term becomes g into z. This term, third term, becomes v square by 2. So this is the next is dividing throughout this equation by g. Okay. So next, p by rho g plus z plus v square by 2g, which is equals to constant. The above equation is called as Bernoulli's equation of flow. So where the p by rho g is called as pressure energy per unit weight of fluid. That is nothing but a pressure head. Next, v square by 2g, that is nothing but kinetic energy per unit weight, that is also called as kinetic head. And z is equals to the potential energy per unit weight, that is potential head. So it is a summation of, the Bernoulli's equation can be given as like this, the summation of pressure head, kinetic head and potential head. So next, see the assumptions and limitations of Bernoulli's equations. What are the assumptions we have considered before deriving the Bernoulli's equations? The assumptions, the following assumptions are made for the derivation of Bernoulli's equation. Very first one is the fluid is ideal. It means that the viscosity is become 0, and the flow is steady. There we are considering the velocity becomes 0. The flow is incompressible, that is density become constant. The flow is irrotational, and the flow is one dimensional. And next is, only we are considering the gravity force and pressure force are only considered. Next, what are the limitations? It is applicable to only ideal incompressible flow. Okay, the heat transfer into or out of the fluid should be 0. The temperature remains constant so that internal energy does not change. The effect of pressure of a mechanical device between two sections is ignored. So these are the limitations of the Bernoulli's equations. Okay. So next, see the, for practical applications, we don't have considering ideal conditions. So we, in our industrial purpose, in any agriculture purpose, in any wherever the fluid is flowing, in that application we are going to consider the real fluid applications. Real fluid. Since the Bernoulli's equation is based on the non-viscous conditions, but all the practical fluids are viscous and offer resistance to the fluid flow. Okay, therefore some losses in the fluid flow between two sections has to be considered. Okay, for practical and real fluid is considered with the losses. Therefore the modified Bernoulli's equation becomes like this. It is P1 by rho g plus pair by 2g plus z1 equals to P2 by rho g plus V2 square by 2g plus z2 plus HL. So what is HL here? So HL is the loss of energy between 2 points, that is 1 and 2. Next, we'll see the applications of Bernoulli's equations, where it is being used. So in a day-to-day applications, we are going to use our Bernoulli's equations to study the rate of flow in a devices. Okay, so the applications are as follows. We are having venturi meter is there, orifice is there, submerged orifice is there, V notch are there, and pitot tubes are there. These are the applications of the Bernoulli's equations. So next, fluid flow measurements. Okay, means the measuring the rate of flow of a fluid. Okay, we are going to measure the rate of flow of a fluid flowing through a pipes or through an open channel. Okay, so wherever the fluid may be flowing in the through a pipe or in an open channel. So what are the devices? Through pipes, for the wherever the fluid is flowing through pipes, we are considering the venturi meters, orifice meters and pitot tubes. For through open channel, if the fluid is flowing through open channel, we are going to consider for the notches and wears. So this is all about today's sessions. If you are having any queries, do please contact the personal WhatsApp number and gets clarified. For the next session, we'll be discussing about applications of all the things of Bernoulli's equation, that is venturimeter, orifice, V notch and pitot tubes.